So this is mini lecture 30. And just like in 29, we look at nodal analysis for a circuit with that we're solving the steady state response that is using the Phasor approach, the Phasor method on top of nodal analysis. In this particular examples, we're going to look at mesh analysis along with the Phasor approach. So we're looking at a case where we're finding responses of circuit in steady state, circuits that have sinusoidal sources, sines or cosines, there could be multiple sources, but one frequency in the circuit. In this particular case, again, very shortly, I'll be pointing out that the frequency in that circuit is 150 radians per second. A little bit of review of mesh, which we've been doing for the last many months in this course here. Anytime we're dealing with mesh analysis, after we prepare the circuit and we know what prepare means identify the mesh currents, put voltages on all passive elements. And then very shortly, we need to know how to treat current sources. And in mesh, current sources, there are two types of cases, if you will, in terms of dealing with current sources. You have current sources that are on the perimeter of the circuit. If I want to be more specific about it, a current source that is in a single mesh, and current source when they are shared, when is a current source shared by two meshes. This is the case when the current source is shared by two meshes. So we learned that, but just wanted to give you a flavor for the kind of situation we deal with when we're dealing with current sources, essentially. The other interesting part in that problem that I want to point out, if you remember what I say, the Phasor method is referenced to the cosine functions. So anytime you have sine function in a source, the first thing we need to do is convert that sine function to a cosine. So very shortly, before I go to the Phasor domain, I'm going to basically say IS is 2 cosine 150t plus 50 degrees minus 90 degrees. Okay, so I'm going to pick up minus 90 degrees. That's how I convert from sine to cosine. The Phasor approach is referenced to the cosine function. So anytime you see a sine in an independent source, you need to convert it to a cosine before you convert to Phasor. Other than that, this particular problem is asking you to calculate IL and IC in steady state. So that tells you this, it's actually the Phasor method is appropriate for this problem. And it's asking you to draw the Phasor diagram for these currents. I'm not likely to ask you that in any kind of quiz, but it's always nice to see that the result graphically. Not likely that you will be asked that. Okay, so hopefully this gives you, this is not a full-on, this doesn't have all of the bells and whistles, if you will, of a mesh analysis problem, but it gives you a pretty solid examples for mesh in that you need to know how to treat a current source. You're going to need to know how to do a KVL around a super mesh. And of course, you have a sine function in one of the sources. So reminding you need to convert the sine function to a cosine. That's what we are accomplishing here. So let's begin that. The first part of anytime you're dealing with a problem where we're using the Phasor approach, we are going to be converting the circuit to the Phasor domain. So you can see in my minus 40 degrees here, that's because I pick up minus 90 degrees to convert the sine to the cosine. So the sine function was 150t. Let's look at it again, was 150t plus 50 degrees. So when I convert to a cosine, it's become 2 cosine 150t minus 40 degrees. So that's what you see the Phasor representation of the source here to be 2 at an angle minus 40, because we converted the sine to the cosine. And then I went on and calculate using the frequency 150 radian per second. I went and calculate the impedance for my capacitor and the impedance for my inductor. Just a note, since we're early doing this, anytime you're calculating the impedance for the inductor, be mindful it needs to be positive imaginary. And anytime you're calculating the impedance for a capacitor, it needs to be negative imaginary. I often write sometimes minus J divided by omega C, just to remind students of that. Other than that, this is actually a typical mesh problem with a current source that's shared by two meshes. So let's begin. We prepare the circuit here. We prepare the circuit, and I apologize for my squiggly current there. We prepare the circuit, so I put these currents. Since I had IC and IL already defined, so I try to keep them in that same direction, okay? And I put I1 here in the first mesh on the bottom left, okay? Then I add voltages on all of my passive element. I'm still following that good practice because I think it avoids you mistake. So I had voltages on each capacitor, inductor, and resistor, naming them separately. According to the case of VC, we had VC, so we're going to keep it that way. So the first thing we do, again, we write the source equation. The source equation is for the current source right there. So I'm going to write, again, back in my days, I had a calculator that didn't handle polar form of complex numbers, so I typically convert them. But one of the first thing I'm going to do is write the source equation here, which is the source is going up here between mesh I1 and IC. So given the direction of the source, that source, which is that 1.53 minus J 1.285, is the rectangular version, the rectangular form of the source in polar form, which was 2 at an angle minus 40 degrees. And that's equal to the current IC minus I1, because IC is going in the same direction as the current source. IC is opposing it, so you have IC minus I1 equal the value of the current source. That's the easiest equation we write. It's one that doesn't require any manipulations. We're pretty much done with that equation. You can count it as 1 for the 3 unknowns that we have. What are the 3 unknowns? The 3 mesh currents, I1, IC, and IL. Okay, so we need 3 equations, and this actually gives you readily an equation for a 3 unknown. This is kind of comparable when we were doing nodal. We put a voltage source between 2 nodes, and we say where the plus is minus the node, where the minus is equal the value of the node, because that's what the voltage source does. The current tries to try to inject a current along that line, so it enforces the current going up that line to be the value of the source. Okay. Next thing we do, we actually write a KVL. So once we realize that, then we're going to write a KVL in mesh IL. This is what I've called in the past a regular mesh. What do I call regular mesh? A mesh that doesn't have a current source. Okay. So it's a regular mesh. So mesh IL is one of those. So I can write a KVL in that mesh. Plus VL minus V1 minus V4 minus V3 equal to 0. Remember, when we do mesh, the polarities of this voltage is entirely up to you. There can be anything. There's nothing accurate. And of course, it suffices to say the mesh, the KVL in that mesh is going to depend on the polarity of the voltage. So it's also correct as long as you're consistent. Where things self-correct is when we're going to write the voltage current relationship that convert these voltages to the mesh currents. Passive sign convention. Okay. So again, the current source belongs to 2 meshes here. That current source IS belongs to mesh IC and IS. So we're going to need to apply a KVL around the super mesh, which is in this. That's the super mesh that you're going to see here. Okay, that I'm pointing out in red. All right. So a super mesh is obtained by merging the 2 adjacent meshes, removing the element on the common branch. So I showed it to you earlier. So I'm going to write the KVL about the super mesh and the super mesh between I1 and IC. So V3 plus V4 plus VC minus V2 equal to 0. The reason we do the super mesh, because we do not know the voltage across the current source, and it's not 0. If the voltage across the current source was 0, the current source would be putting no power, would be dead. Okay, we don't know the voltage source, so we essentially use the relationship that the current is creating between the mesh current, the source equation, and then we look at the larger loop, what we call the super mesh, and create the relationship between the voltages across the super mesh. That's standard stuff we were doing in the first month and a half of the course. So in doing so, we have our 3 equations. What are they? We have the source equation that come from the current source. We have the KVL in this regular mesh here. Okay, and then we have the KVL in the super mesh that's made of mesh I1 and mesh IC. Those are the 3 equations we have. The rest, we're going to write the voltage current relationship, essentially for each voltage on the passive element. Anytime we do this, we're looking at passive sign convention. Is the current entering the positive terminal? If you look at VL, for example, VL, the current is entering the positive terminal. So VL should be J450 times IL. But if I look at V1, the current is entering the negative terminal of V1. So V1 would be minus 5 times IL, which is what. And similar for V2, I1 is coming this way. That's how I1 is coming. So I1 is entering the negative terminal of V2. So V2 would be minus 10 times I1. And then anytime you have, in mesh, anytime you have passive elements that are between two meshes, you need to pay attention. You need to have both contribution of both mesh currents, and you need to pay attention which current is entering the positive, which current is entering the negative, if any. So for example, in the case of V3, we have V3 is equal to 20 times I1 minus IL, because I1 is entering the positive terminal of V3 and IL is entering the negative terminal. That's what you have that. Okay. For VC, VC is just the impedance times the current, because IC is entering the right way at the positive terminal. So it's minus J20 times IC. And finally, for V4, again, V4, the 6 ohm is shared by two meshes. So you need to have two currents. Looking at the passive sign convention, V4 is 6 times IC minus IL. And finally, VL is J450 times IL. We take all of these voltage current relationship, we bring them into the 2 kVL equations, and essentially we end up having three equations, three unknown. This is the source equation, the original source equations for the current source, and this is KVL1 and KVL2. Once I put all those voltage current relationship, and then we basically collect terms. We said before, the difference between nodal and mesh, we don't have to put into the same denominator, which is essentially sum up those terms for I1, IC, and IL. So it tends to be algebraically a little bit easier to deal as opposed to nodal. I typically put that in a matrix form. The intent of doing this is to essentially encourage you to use your calculator, or frankly, any kind of website that can handle complex matrices. And we calculate the current I1, IL, and IC. Okay. And we need those currents finally in polar form, not just in rectangular form, but in polar form. And I'm showing them to you. So again, in terms of IC as of, the real problem asks you IC as a function of time. Once we know the phasor solution for IT would give us the magnitude and the phase, we can write the real problem that you were asked to solve for IC of t, which is 1.48 cosine 150, which is the frequency of the source, t minus the angle of 10.5, which we calculated. Okay, so that gives you a pretty good, this is not the hardest problem you can have in mesh, but it's a pretty robust, it has a current source between two meshes, forcing you to remind yourself of how to handle super meshes and so forth. Again, we can do the same thing for IL. Again, once we have the IL in polar form, we can use the magnitude and phase to write the real solution. And then finally, this is what we call the phasor diagram, plotting it in the real and imaginary using the angles and the magnitude to express the phasor diagram. So this is a pretty solid example, not too complicated, but solid, using mesh analysis overlay with the phasor approach for sinusoidal circuits.